Yes. So you can, we'll consider the case first part of the course. Okay, let us begin. So discrete maps was first given more importance when Robert May started studying them. Okay, Robert May, you can see, he's a biologist basically, and also a mathematician, like mathematical biologist. So he you can read it. So he created the new field of chaotic dynamics in biology. Okay. So what he did, he in 1976 he published his most popular article titled "Simple Mathematical Models with Very Complicated Dynamics." And in that paper, you can download this or request library to issue a copy or issue a copy. Okay. So in that paper, you will see that he has suggested an example of like population dynamics. Okay, that we'll see very soon. So in Nature, he published this, and he showed that first order nonlinear difference equations. Now you can make the connection, no? Difference same as recurrence equations, which we talked about last time. Xn plus 1 equals to f of xn. Okay, that is a recurrence relation. And he showed that yes, they show a astonishing array of dynamical behaviors ranging from stable fixed points to chaotic regions. Fixed points, what is a fixed point? When it is stable fixed point, chaotic, all will come after this. Okay, we'll see. No need to worry. And he is now doing virus dynamics. Of course, he is not there anymore. He was doing virus dynamics, mathematical foundation of immunology and virology. Trained as a physicist at Sydney University, Australia, where he received his PhD. He moved to biology for good in 1973. Okay, and of course, then carried out studies in Oxford and Princeton. So this part I have taken from the book named Discrete Chaos by Saber Elaidi, who is currently a professor at Trinity University. So he has helped me a lot actually in participating in different international conferences. He helped me last 2 years to participate at a conference in France, and it was quite good. He's a very kind person. So he also works in mathematical biology and dynamics. Okay, with that, I think I will tell you what we had discussed last class, and then we will move to the what do you call that, computational aspect. Okay, let me start with this. So to those who were absent last class, so we will be discussing a particular kind of system known as discrete maps. Color okay for you? Yes. Let us do green today. Okay. So a discrete map is given by xn plus 1 is f of xn. Okay. What does it mean? To visualize this, you can visualize, put n equals to 0, then you have x naught here. X naught is the starting point. So this is referred to as initial condition. This is referred to as initial condition because this is the starting point of your dynamics, of your any of your system, x naught. Then you put x naught here. Then if you put x naught into this system, what will happen? It will be a new point, which is f of x naught, isn't it? Yes. And what is f of x naught? It is x1, isn't it? So x1 is f of x. So from x naught you went to x1. Similarly, how you went there? You applied the map f. You applied the rule f. Okay. Now you go to, sorry. Yeah. Now you apply the map f again. You go to the next point, isn't it? That is x2. What is x2? Can anyone tell? F of x1. F of x1, isn't it? x2 is the future and it depends on the past, x1. You got that idea? Just use common sense. Okay. Now you do again and again, it will go to new point. Why I am not doing in a linear fashion? Why the points doesn't go like this in a linear fashion, and why it is doing non-linear? Because f can be non-linear. F can be linear, f can be non-linear. I am taking a general case. Case over here. Okay for you? Yes. Now let us start with a simple example where I will show that you can, in your notebook, can do all these things. Then I will give you another example where you cannot do in the notebook. Then we have to go to computation. Okay. How about xn plus 1 is axn? Okay. It is a linear map. It is a linear map, isn't it? Yes. Why it is a linear map? It is just the power of 1. Okay. Can anyone tell me a starting point? X naught? Maybe the second row can tell me. There Anandik or Halima can tell. What can just tell me any x naught value? Any value? Huh. 5. So let us start with 5. Can anyone tell me, Halima can tell me the value of A? Any value? Real value? 7. Okay. Okay. So yes. So since x is like a real number, x is real, x is a real number. So how can you visualize what is our aim? Our aim is to understand the time series of this x. How x evolves. How x evolves is our aim. That is our aim. Okay. So in order to understand what we can do, just draw a line, a number line. This is 0. Okay. Now Anandik start from x naught, that is 5. Yes. And Halima has set the parameter A. It's a parameter. You can control it. A equal to 7. Okay. So can any of you tell me what is x1? A times x naught, isn't it? What is A times x naught? A is 7, x naught is 5. So it is 35. Okay. So you can see it took a very huge leap just to be in the boundary. I am doing this 35, but actually this is not 35. Okay, that you can make sense. So how it went to a very big leap? This is a big leap. Why? Because Halima has set a very high parameter, 7. If Halima would have set 0.1, it would be 0.1 into 5, that is 0.5. So it will be very close to 0 around. Okay. So see, since she set 7, it was a huge leap, 35. Now what is x2? A into x1. Yes. A is 7. X1 is 35. Okay, what is this? Okay, done. Now 245, you can imagine it is very far. Okay, still I have to draw here. Don't worry about it. Okay, but it is a very big leap. Can you see the difference here is 30, but the is around how much? 190. Oh yeah, sorry. Is around 210. Good. So now you can see this difference is bigger. Since A is a parameter greater than 1, like it is going outside. So if you continue like this, can you tell what is x100? It will be way out. So it is going outside. So if you take 10,000 or something, it is diverging. It is going towards infinity. The values are increasing continuously. Okay. Now, if you take A to be 0.1, okay, if A is 0.1, then what is the case? If A is 0.1, maybe this one, then what is x1? 0.5. Yes. What is x2? A into x1, that is A into 0.5, that is 0.05. Yes. What is x3? 0.1 into 0.005. Sorry, my bad. 0.005. Yes. Can you see what is going on? So if I draw this now, okay, if 0 is here, 0 is here, 0 is here, and you started from 0.5, but now the parameter is 0.1. So you can see suddenly it became 0.05. then it came nearby here, 0.005. So the transitions is like this. Yes, it is coming close to 0, isn't it? If you take x 10,000 now, it will be reaching 0. So x is converging towards 0. Yes, so you can see this idea over here. If you take a greater than 1, it is diverging. If you take a in between 0 and 1, it is converging to 0. But the main idea now, can you put this model in terms of population biology? I am saying this is a population biological model. Is it a good model? How many of you saying it's a good model? Is it a good model? Is it a good population model? I am saying that population today in India 2025 depends on 2024. Okay. Yes. There are a lot of reproductions. So there will be 2025. You can imagine people like there will be a lot of births. So it will increase, and it will. I should not say it will increase. It will vary. Some increase, some decrease. So it will vary. Okay. So therefore, in that perspective, I am asking: is this model xn plus 1 is a xn? This model number 1, is it a good population biological model? It is not. Why? If you see in both of the any parameter you set, any parameter value a, if it is greater than 1 or more, like -3 also or 3 also, the population is diverging, and you don't see the population diverging in Earth on Earth. Yes, population is constant. Okay, it's changing, but for a particular time instant. If I say a t equals to a time 11:30, what is the population? If there is a software which can calculate the population at 11:30, then it is constant. At 11:31, it might change. Okay, but at particular time instant, it is constant. Okay, so therefore, it is not a good population model because either the population is 0 or the population is going to 0 or the population is going to infinity or is constant. If you take a equals to 1, if you take a equals to 1, what happens? Xn plus 1 equals to xn, isn't it? So if you start with 0.5 every time it will be 0.5. X 100 without computation, 1000 also is 0.5. Yes. So it is not a good population model because you know population can never stay constant. Okay. It doesn't stay constant. Yes. So therefore, there needs to be a population model to create. Okay. So this is where Robert May created a population model. Okay. In his paper here, I think simple mathematical models in with very complicated dynamics. I ask you to read this. Okay. He developed a mathematical model. He came across this. So basically, he came across a model, namely this one. This is known as logistic map. It is an example of a population dynamical model. Population dynamical model. Okay. Now, instead of xn plus 1 is axn, they noted it down. Xn plus 1 is some parameter r, they call xn into 1 minus xn. Okay. Previously, due to it was only increasing or decreasing towards 0. Now they have created this factor over here, 1 minus xn, due to which the reduction will also happen. You understand? Xn and 1 minus xn. Xn is not a population. Xn here is not a number like you will see 10,000 or something. It is a normalized quantity. It is a normalized quantity. Like maybe xn plus 1, you can think of number of male to the total population. So it is a real number. So it is a number you usually see, but it won't be in the scale of range like 10,000 or 20, 30 like that. It is a normalized variable. Okay. In data analytics, you learned about normalization. How you normalize, like say number of individuals who caught cold this week. How you will say? Saying a number is hard, but if you say number of individuals, students who got cold divided by the total number of students, then you will get a percentage of the students who are affected. If it is more than 50, then we are in a danger zone. That means it is spreading high. Yes. So sometimes it is not the number that is important, rather it is a percentage that is important. So therefore here it is a normalized quantity. Okay. Now from here I think our nonlinear dynamics starts. Okay. So can I ask you one thing to do in your Python now? Okay. If you want to do by hand, you can do, but I don't recommend doing by hand because it's already now non-linear. It's not simple as ax. Xn plus 1 is axn. Okay. So I ask you, suppose you start at 0.2, x naught is 0.2, the starting point is 0.2, and say your parameter r is 2. Okay. Can you plot, can you show me the time series? How x is evolving? That means I want to know what is x1, what is x2, x3, so on till maybe 1000. Can you do this in Python? It is very hard to do in your, what you say, you can use a calculator to do anything, but I suggest that to see it computationally, I suggest you try in Python. You got the idea how you will implement this in Python? Create an array x. Create an array x. Okay, create an array x. This is create an array x. Okay. First element of the array should be the initial condition x0, which is given to be 0.2. Based on that, you find what is the next element. After you get this element, find what is next. What is the next element? Yes, you got the idea. Store this array and plot the array. So every time you plot, show it with a dot and connect it with a line. Something like this, something. Show it with a dot and connect it with a line, dotted line or anything you prefer. Can you do this? Hmm? Queries? Okay, so yeah, you can see here like uh, all the necessary things are done as per your first semester course. Then I'm defining this logistic map, and I have taken R and X as parameter. Okay, X, what is R? R is a parameter. What is X? It's the initial condition. So if I give an initial condition, it should evaluate what is R X into 1 minus X. Yes, and that's what it should return. Return R into X into 1 minus X. Yes. I have set the different parameters r equal to 3.5, but I can change it to 2. Yes. So r is the growth rate in terms of population dynamical concept. Okay. And this is the initial value which I have taken 0.5. We are taking 0.5, is it? Or 0.2? Okay. And number of iterations, how much? 1000, but let us take 10 and see how it evolves. Then we can change this to 1000. We do here, I have initialized the x values of the array as np zeros. So an array with all zeros set in. Okay. It's a predefined array already. So I have allocated the size already to the array. And what I am doing now, the next thing I am doing is x value 0 is x naught. Okay. X values of 0 is x naught. That means the first element of the array, I have chosen it the initial condition, that is x naught. Is it okay with you? That's how it should be, right? Then what is our next step? Then we should predict what is the future value of under the logistic map. That is, what is the first value of the array? Yes. So what is x1? Is r x naught into 1 minus x? Yes. So therefore, how you do it? Instead of keeping the function like rx return, how Shweta has done, like I went to encapsulation. Like I use encapsulation. Like the user should not see the function, rather he should call the function. Okay. So rather you can put this value, the future values of x array, x values as logistic map, and what are the functions r and I min. Okay, these are the initial condition for the function, and it goes to this function, right? Defined above. I think did you see already? Yes, you saw already this function. Yes. So now you see through this for loop where my cursor is, you are storing the future iterates of the x, and that's you need to plot. That's it. Okay. So now that is done, and now is the plotting. Okay. I have done a yes, I have done this thing, subplot x values. These are all plotting comments. The more you learn about this for data visualization, the more it is good. So you should be seeing this more often so that it will be fixed in your mind. Hmm? So x label, what should be there? Iteration, yes. And y value is the x value, yes. Fine. So this is how it is. You can see this is for 10 iterations. Okay, this is for 10 iterations. The more I do, if I go for 100, okay, yes, you can see this. Okay, what is happening? What is happening here? Can you see? Initially, when I considered 100 or 10 numbers, it was oscillating. The data was oscillating. But what happened if I do till 1000? 100 it is, sorry, 100 it is reaching the, no, maybe 5, it is reaching a steady state. You can see. Yes, you can see these are the, where the kinks are. Where the kinks are, there it is a new point. Okay, and I'm connecting the points by a line. Be very careful that in between these 2 points, there is no value, but I'm just connecting by lines. I can connect by points also. So the actual data is something. This is the actual data. This is the actual data. I'm just connecting by line just to make you a visualization. Okay. Now I think it will be a good thing. Now I suggest you all guys to change it from 2 to something new. Say 2.1, how it is behaving. This is the parameter, growth parameter we are changing. Now you can see, yes, it is still reaching the steady state. Let us increase the iteration to 100 just for visualization. Okay. So you can see it is reaching quite the steady state. Yes. For 100 iterations, you can see initial value, it started to change and then it is steady state. The population is constant. Okay. Which is very unusual for population dynamical concept. Population is constant. Population should be like a bit oscillatory with time. Yes. With time, it should be keep on changing. Yes. How about any 2.3? I'm changing the parameter very slow because this nonlinear dynamical systems, you have to give respect to the parameters. You should not change the parameters too very large. Okay, you can't change it like it. They're very sensitive. So yes, still it is undergoing a steady state. Let us change 2.5. Still steady state. Anything else can suggest me? 2.8. Yeah, I'm playing with the model. Yes, something interesting. Something interesting is here. Okay. So even though it is going to a steady state, but the way it is reaching the steady state is something interesting. How it is reaching the steady state, you can see here. You can see over here that it is oscillating. This point, from this point to this, then it started and went to steady state. It's the transient. We call it as a transient. Okay. Before reaching the steady state, it did this kind of oscillatory pattern. So this is a transient oscillatory pattern. Transients. Okay, those who have a bit of background with engineering or something, they would know transient. Like you discard some initial stuff. These are not accurate. You know, to see something final, what you do. So in the mess, I will give you an example of the mess. New students have joined. Okay, now it is hugely chaotic. Now it is very chaotic. Some are sitting somewhere, some are eating somewhere. Like lot of people, lot of drama, like in the mess hall. Okay, so but it will continue for only 1 or 2 weeks. I guarantee you that after 2-3 weeks, maybe 3 weeks, okay, you will see that the pattern is very smooth. Okay, now if all will come in line, everyone will get within 1 minute the food and they will eat. Okay, now you have to stand in long queues and huge things happening, but this is the transient. This is the transient because it is a network system. We will come now. All people now it's a network system. It's not the dynamics of only Anandi. Okay, it's the dynamics of different people around. Okay, lot of different minds are there, and they are coming and eating, taking the plate. No one is synchronized. Now, after 3 weeks, they will know who is he, who is she, and then things will start synchronizing. They will form groups. They will go together to the mess. They will start eating. This is one of the example why in the common hall you clap, and suddenly everyone is clapping at the same rate. Okay, you don't see someone is not clapping, someone is very slow. Like you see it uniform. That's one of the examples of synchronization. So therefore, this transient, I'm explaining you the meaning of transient in mathematical sense. Let us go. Let us play a bit more. How much will do 3? Interesting. Yes. So as you vary the parameters, you can feel what is going on. Okay. So what is going on? So it is these are the transients yet. These are also the transients. They're trying to reach to a 2 state. Okay. It's a periodic orbit. What is a periodic orbit? They're oscillating in between 2 states. This and this. Okay. At one instant it will be this point, at the other instant it is this. So and they're the same. They are the same. But if you see throughout, what is this? What is this? The beginning phase. What is the beginning phase? It's a transient. Usually we don't take the transient. Don't take it. But for a beginner class, I'm showing this. Okay. The final output is this. The final output, I will say what is the final output at after 1000 days. Then this is the output, 2 period 2. Getting? Okay or no? Okay. Okay. Any queries, please ask. It's not like you don't need to ask. You just ask. 3.2, let us take. Yes, now you see no transient at all. Now they were showing some parabolic kind of transient and going towards a steady state. Now you see from the beginning onwards, it's in a steady state. So you see how the transients are playing the role. Yeah. Can you be louder? X. Some X is there. Grids. It's the population X. So X is a state. Okay, X is a state at a particular time instant. At a particular time instant, you will see one population, but it's a period 2 orbit. Um, no, I think you will be clear. Maybe it needs one more class. Just wait for one more class. It will be clear. I know what you're thinking. Like why on the same line you see kind 2 points something. It will come. I'll come to that. Just now you can appreciate the patterns you are seeing, but deep we will come to. So first, to what you saw, we saw a straight line, only one straight line. That means it's a steady state. Whatever you do, you are always at that point. That the 2 points are oscillating in between the two. So it's a periodic point of period 2. Okay, it is jumping from here to here, here to here, like a pendulum, starting from 1 to second, and again coming back, again starting, again coming. Period 2. So we'll see this. We'll discuss detail. Okay. Let us go for now. Just see how it is varying. Suppose 3.4. Yes, still if a bit of transient here, you can see, and then period 2. Fine. So period 2 is persistent. Like even after a lot of period changes, parameter changes, it is still there. How much you suggest? 3.7 maybe? 3.6? 3.6. Yes. Something new which you have not seen yet. Okay. Let me draw the lines so that you can appreciate it a bit more better. Now I ask you, do you see a pattern in this? Is there a pattern or there is no pattern? There are two questions. Is there a pattern here or there is no pattern? Hmm? Is there a pattern? How many of you are saying there is a pattern? How many of you are saying there is a pattern? Can you say why there is a pattern? Why there is a pattern? Why like what sense did you think that there is a pattern? Yes, some of them are same, but yeah, like there is no periodic pattern. There is no periodic pattern. Yeah, of course there is. If you see the whole time series, these guys are at the same height, but then in between that, this see this one there is a pattern like this. It doesn't repeat anymore. If you see any point you take spend a bit of time, it doesn't repeat. Yes. So this is what is chaotic. Okay, it doesn't repeat itself. It's not periodic, not reaching a steady state. Okay, it is a chaotic dynamics. Okay, you can't predict. Can you predict how the next point will look? Let me try to plot. I think 200, but it will be clumsy. It will be clumsy. Yeah, you see, still no pattern. Still there is no pattern. Are you like convinced with this one? Or are you convinced with this? Yeah. Let us play a bit more. 3.9, 3.8. So I'm saying how the parameter is your is the best example of your parameter. Parameter is your AC remote. Okay, AC remote. If you there is a button for decreasing or increasing the temperature. So this is how in your you have a remote and parameter R is there. You press the button, parameter R is increasing, and you're seeing different dynamical behavior. A fixed point like a straight line, or maybe period 2 orbit like a two dots, two lines. Okay, chaotic behavior where you see random fluctuations. Yes. So this is a kind of a parameter. We say those quantities as parameters. Now you see here, it is still chaotic, but still chaotic, but still something happening here and here. Some different pattern. You did not see that before, is it? Is it? Did you see that before? I don't think you saw something like this in between before. So that is what is chaotic is. Okay. All right. Maybe let us keep on increasing. Maybe 4. Yeah. Now you see like some gaps are of this kind are happening. Some gaps are coming in, isn't it? Every graph is different from the previous graph. That's the beauty of this. Like every time you change the parameter, something new is going to happen. Although in a chaotic regime. So 4.2, yeah. Now in 4.2 you see something else is happening. Okay. So it's in a parameter you can't predict. You can't predict this. And it is a very simple nonlinear equation. It is a very pretty simple nonlinear equation. Rx into 1 minus x. Everyone, even class 12th or class 10th student can do this, find the roots or anything. It's a quadratic. It's a quadratic. Okay. But still, it is showing chaotic behavior. And that's what this paper is about. Simple mathematical models with very complicated dynamics. Okay. So we will spend a bit of time with this model, playing with this model, because this is the perfect candidate in any course. This is a perfect candidate to start with. Okay. So yes, so this is one of the things, and yeah, um, yes. So do you understand what we are interested in? you saw a lot of graphs, you saw many things. What we are actually interested in. So given this map, xn plus 1 is r into xn into 1 minus xn. Okay, we are interested in understanding these concepts: x1, x0, x1, x2, x, capital N is a large number. In other words, we want to understand. Yes, let me this. Yes, we want to understand the long-term evolution. Okay, the long-term evolution of the logistic map. That is how the trajectory behaves. Okay, how the trajectory. There is a name known as trajectory, but usually it is used for continuous systems. For discrete maps like this example, you use the word orbit. Okay, how the trajectory or orbit evolves over time. So throughout the course, this is the basic question we will ask. This is the basic question we will ask. Given you a system, we want to understand how the long-term evolution of a system is with like time, how that orbit behaves over time. What is orbit? Orbit I will denote as O of x. Okay, just a set. I want to just a set or an array for your case in computational knowledge. It is the collection of these variables x0, x1, so on till say x capital N, where n is large. Got the idea? Hmm? So this is known as the what you call the orbit trajectory. Okay, and this is the simplest nonlinear map, and the nonlinearity is quadratic. If you see this guy is r xn minus r xn square. This is linear. First term is linear, second term is nonlinear, xn square. Okay, got the idea what is going on? Tell me, like, we want to explore this map, so we will spend 2-3 classes on this map. Okay, so why the map does like this, but why it does? If the map does like this, but why it does like this? Yeah, the map is showing like this and it is a very simple model, but why it is doing like this? That we have to understand. Yes, that's the part of the course. Like, that's what nonlinear dynamics. Now you can understand. Can you understand the term nonlinear dynamics now? This is nonlinear, and dynamics means it is varying over time. Every iteration it is varying. Yes. So therefore, it is nonlinear dynamics. Okay. Since this model you cannot perform, would you was it possible for you to understand the concept I showed of fixed point, periodic point, and chaotic just by doing on a paper? No, it's not that possible. It will take full day for you. Okay, 10,000 iteration full day. Okay, so therefore computational knowledge is used. Computational power is used to understand this simplest map. It is a very simplest map. Why Python is needed? But it is needed. That's where the beauty of this subject lies. Okay, so these are very simple models where you might have seen these kind of things, but you did not see this behavior often. Okay, so just before we close this, one more thing just I'll tell. Okay, so you can see this is the y and this is the x. Now forget about the recurrence relation. Forget about the recurrence relation. Now we are not looking into this. Now we are not looking into this concept. Rather, we are looking into this function here, f of xn. What is f of xn? F of x is Rx into 1 minus x. Yes, you got that idea. Now we just plotted here y equals to Rx into 1 minus x versus x. This plot. Okay. Now we want to understand the function. In order to, now we have seen that this simplest nonlinear function is doing very complicated dynamics. In order to understand, we have to plot the function. Okay, fx. So this is how it looks, the red curve. You can see our this x here in the recurrence relation will always vary in between 0 and 1. Population varies in between 0 and 1, doesn't make any sense. But as I told you, x doesn't represent population, but rather this is a normalized population. It is a ratio. It is a ratio. Okay, standardization, data standardization. So this is a ratio. So x is belong to 0 to 1. It is normalized like that. As you can see, this is the curve. Okay. Now the maximum is 0.5. Can you prove it? Sorry, can you prove it? Maximum is at 0. Yes, you can prove it. Class 12th. Class 12. Just apply the differentiation, set it to 0. Rx minus Rx square, maybe x minus x square if R is equal to 1, R equals to 1. Okay, then put d by d. Yeah. Then put d by dx of this equals to 0. What you get? 1 minus 2x equals to 0. X star, I would say, x star is 1 over 2. So maximum is at 1 over 2. And you exactly see that here. Maximum is at 1 over 2. Yes. So that's how. This is a special function actually. This is known as one hump function. Okay, it's a unimodal function. You don't need to know about it much. But for those, for DSES students, I would like to say this function is pretty important. It's a hump. It has one hump. If you can have functions with two humps, the two hump functions. Okay, and many dynamics changes in this case. This is one hump. Unimodal function. Okay, this is two hump. Don't need to know about it, but just I told. So you can see how the function changing is important. Okay. Next class we will see what is a fixed point. What is a fixed point and why you got that steady state and why you got that period 2 state. Okay. There are a lot of other information there which I hoped I could have covered today because it's really interesting computationally. Something next class, what is coming next class? We will learn something known as cobweb diagrams, computation. Okay, you will visually see why, depending on the function, it's only on the function behaving. Due to the function one hump, because the shape of the function is one hump, it is behaving chaotic. You will see. So next class, everything will depend on this function. I will draw a straight line, then I will draw some cobwebs and show that graphically you can show that you are reaching a fixed point. Graphically, you are reaching to a period 2 point. Graphically, you are reaching a chaotic state. Everything just depending on this graph. And you can appreciate how beautiful this is just by a single graph. Okay. No computation will be there. Only, yeah, well, of course, you'll see computation, like how to do that cobweb in computation. But I will show you how in your mind, if you know the technique of cobweb diagrams, you can predict that there is a fixed point, that there is a period 2 point, that there is chaos. It's very interesting. I want to teach now, but I'll keep to the next class. But what is coming ahead? So I'm just telling it like in a series, web series, the things are there. What is coming ahead? So what is coming ahead? So we will learn bifurcation diagrams, how to draw this kind of diagrams. So this is a bifurcation diagram and this is indeed fractal. Okay, you will see things are looking like this. Okay, and why it is a fractal. Why this simple nonlinear equation is giving you self-similar behavior. Okay. Be present for next class. There is a lot to explore for this behavior. Okay. If you give me time, I can. So it's quite interesting. Like before I finish off, I just tell one more thing. The transients you were seeing, this is just a plot where we plot on x-axis the parameter, okay, and y-axis is the x variable, okay. So here I did not eliminate transients. I did not eliminate transient at all. Therefore, you see these oscillations here. You can see my mouse here. You can see these oscillations here, here, here. Okay. Why this happen at these points only? Why not they happen here? Why they did not happen here, but they happened somewhere here? Here. Why? And here I did not eliminate transient, but the moment I eliminate transient here, mm, yes, the moment I eliminate transient, you will see it will take a bit of time. This program will take a bit of time because it is computationally intensive. But anyway, we'll just see the output and close the class. Why it is computationally intensive next class. Okay. So even for a simple nonlinear equation, it is taking such amount of time. So this is where I want you to have a feel that the world is not governed by the linear systems. It is governed by nonlinear. Okay. So it is done. Now you can see a clear picture. It is something clearer than the last time, isn't it? Something more clear. Now you can see that some history is going on here. Many history that we will see for the next class. That is the I forgot that name. What is that? Huh? No, that is there, but I forgot in a web series they say no, they give the final what is happening ahead. No, 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 no. Post credit scene, yes. Post credits. That is the post credit. Yeah. Okay, so yeah.